Hello. In the last video, we showed that you could find generally the gradient for the curve y equals x squared. Here's the curve. We found generally, using our little triangle here, our little red triangle, that m equaled 2x. So whatever the value of x was at the point at the bottom left here, this point here, that one there, the gradient was equal to 2x. Let's see if we can extend that now and look for a general pattern. Okay, let's look at the gradient of the curve y equals x cubed. And again, I'm going to follow the same method. So our starting point is at x, and therefore our y value is x cubed. And then we're going to move up along a little distance h, small distance, and therefore our upper point is our original x down here plus h, and therefore our y is x plus h cubed. We know what our along is, we need to find our up value. So that's a difference in the two y values, isn't it? So the y of the upper value is x plus h cubed, y of the lower value is x cubed. If we expand this bracket, we can do that by the grid method twice. We had the answer for the x squared earlier, didn't we? X plus h squared, and we could just multiply by x plus h, and we end up with x cubed plus 3x squared plus 3x squared h plus 3x h squared plus h cubed. That's our bracket, and then we're taking away our original x cubed. So once again, these two terms effectively have cancelled out, yeah? The big numbers have cancelled out. So we get left with this term here is 3x squared h plus 3x h squared plus h cubed. You happy with that? And again, using our definition of a gradient, which is up over along, well, we've just found our up value is that one expression, and we're going to divide it by along, which was h. So the first term is here is going to be 3x squared h divided by h. So we get 3x squared. Now again, as we saw in the earlier one with x squared, and we started with y equals x squared, the first term no longer is not dependent on h at all, is it? The second term here, 3x h squared divided by h, is therefore going to be 3x h. And our third term here is going to be h cubed divided by h, which gives us h squared. Yeah, so we've now got three terms, two of which are dependent on h and the other one is not. Okay, then we'll follow our concept from before that we're going to make our triangle smaller and smaller and smaller and smaller and smaller. So that means our h is getting very, very, very small. And in practice, it means that h is becoming 0. So when h becomes 0, well, the first term remains 3x squared. The second term, 3x times 0 is 0. And the third one, 0 squared, is 0. So we're left with a gradient of 3x squared plus a load of zeros, which is 3x squared. So we've just proved then, for the curve y equals x cubed, the gradient at any point, and value x, is 3x squared. So again, if we start at x equals 3, then that's going to be 3 squared times 3 is going to be 27. If we started at x equals 2, then the gradient would be 2 squared is 4, times 3 is 12. Yeah. And also, if we started at minus 2, then minus 2 squared is still 4, and also 4 multiplied by 3 is 12. So if we have a generalized expression for the gradient at y equals x cubed, and I'm just going to reshape this because actually the curve would go like that, wouldn't it? Y equals x cubed. Okay, and we can do exactly the same thing for y equals x to the 4. We can start with our point x, and therefore our y value is x to the 4. We can move along a little h, So we've got x plus h, and that is our new x value, and therefore the y value is x plus h to the 4. We know what our long is, it's h. We can find our up value because that's going to be the difference of the two y's. So we now got x plus h to the 4 minus x to the 4. If we expand this bracket again using the grid method, we've got x to the 4 plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4, and then we're getting that's the bracket, and we're taking away x to the 4. So again, the first two terms, the big start points cancel out the big point values, so we're just looking at the difference now, aren't we? Okay, and once those two are cancelled out, we've got 4x to the 3 x cubed h, 6x squared h squared, 4x h cubed h to the 4. When we come to calculate the gradient, again we've got our definition up over along, we've got our upper term we just calculated, and we're going to divide, that's that one, and we're going to divide it by h. So the first term is 4x cubed h divided by h. Well, that cancels out the h, doesn't it? So our first term is 4x cubed. Our second term here is got h squared divided by h there in the right hand end, so that's going to become 6x squared h, and the next term's got h cubed divided by 3, so that's going to be 4x h squared, and finally we've got h to the 4 divided by h is just h cubed, isn't it? And once again we've got one term here which is not dependent on h, and all the other terms are dependent on h. So when we follow our logic of making the triangle very, 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 very small, in the practice h becomes 0. So what does that do to the expression? Well, we're left with our 4x cubed, aren't we? And then we've got 6x squared times 0 is 0. And then we've got 4x times 0 squared is 0. H squared, 0 squared. Yeah, and here we've got 0 cubed, which is 0. So once again, we're left with our 4x cubed. We're only left with our first term. Can you see that the other three terms become irrelevant and become 0 because they're all dependent on h? So we've now proved to ourselves that for the curve y equals x to the 4, the gradient m at any point is 4x cubed. Yeah, so again, if we start at the point x equals 3, we'd have 3 cubed is 27, and then we'd have 4 lots of 27, which is 100 and what's that? 108, is it? Yeah. So, and we could do that for any point, we can find the gradient. Okay, so let's have a look at the pattern now, shall we? What have we just seen? Well, for the first one, when y equals x squared, we had m equals 2x. Y equals x cubed, we had m equals 3x squared. And for y equals x to the 4, we had m equals x to the cubed, isn't it? Okay, so let's have a look and break this up, shall we? So the first thing is, what's the coefficient? Well, here we had a power of 2 in the first one, x squared, and the coefficient was 2. Here we had x to the power 3, the coefficient is 3. And in the third curve we had x to the power 4, and the coefficient was 4. So so for any yx, and I'm going to call it to the power n, then m equals, well, the coefficient is the power, isn't it? Here we go. And the second thing is, what's the power of x in our gradient? Well, here we had a power of 2, and our gradient had a power of 1, didn't it? We don't usually bother to write it, but that's got a 1 there. And here we started with a power of 3, and we ended up with a power of 2. And here we had power of 4, and we ended up with a power of 3. So each time, whatever we started with, our power, we end up with a gradient which has got, take 1 off, haven't we? So 4 becomes 3, 3 becomes 2. So therefore the gradient m is going to be n times x to the power n minus 1. So what we've done is create a general expression here. So to summarise, if we want to find the gradient of a function, we can do this by differentiation. That means differences, little differences. So we create a little triangle, a very small triangle here, yeah, at the point we're interested in. And then we find the gradient, which will be a very small up over a very small along, and then we make those very small things effectively get smaller and smaller. So in practice, our little h that we've been working with, we make 0. And we could do that for any function out there that we wanted to do. We could follow the same method through. What we found though in our work is that we've generalized the gradient for a simple power relationship, y equals x to the n, is going to be m equals, the gradient m equals n times x to the n minus 1. And that's our basic idea of differentiation and how we use it with these curves, and we can use this for polynomials and generalize it. Hope that's of use.